In this lecture, I will introduce image transforms. Let us consider image as a continuous function. It is a two-dimensional function and a point is in the two-dimensional real space. And let us consider a set of basis functions which are also a two-dimensional functions. We can represent it as a set where each function is given by say b I x y. You should note that this could be the functional value could be either in real or in the complex domain. We can represent we can expand a two-dimensional function f x y using b as a linear combination of these basis functions as it is given here in this form, that lambda I into b I x y, and where I is the indexes of the basis functions as given in the set. So, the transform of f with respect to b is given by this set of these coefficients which are lambda i's, and these are called coefficients of transform, and we can represent the function as a linear combination of these basis functions, where the coefficients of linear combinations are listed here. So, you can see that this is an alternative description of the image. Instead of representing the image by the functional form of f x y, I can simply represent it as a list of coefficients, or even these coefficients can be a function of indexes. So, indexing may be multidimensional. For example, for a two-dimensional function indexing, we can use two such indices to denote a coefficient, and in that case we can see that this function can be expanded in the form of a linear combination of two-dimensional functions, and we can have these double summations in this representation. So, one of the advantage of image transform is that these properties of basis functions, this can be extended in the analysis. Let us consider a particular type of property which is very useful when these basis functions they have this property. This property is called orthogonality property, and if I expand the function in terms of this orthogonal basis functions, then we call that expansion as orthogonal expansion. We will consider our discussion following up the discussion on this image transform. We will restrict our discussion to one dimension first, and later on we will see that these properties can be easily extended to two dimension. So, we will understand the one dimensional transform initially. So, one of the thing that we would like to define here, this operation inner product. So, inner product is a binary operation where two operands are two functions. You can see that this function f x and the another function g x. So, it is the product of these two functions and integral of these product values at every point in the space x. Now, of course, in this product there is a there is something you should note, that it is not a simple product. It is a product of function f x with the complex conjugate of g x, and that is we are considering here. If both f x and g x functional values are in the real domain, then complex conjugate itself will be the same functional value. So, then we can write it as f x into g x dx. So, orthogonal expansion it is possible when the basis functions they satisfy certain property. That means, the set of basis functions it satisfies this particular property of orthogonality. What you can see that inner product of any two different basis functions, that should be equal to 0, whereas inner product of the same basis function will have a non-zero value and which is a positive value. If this is true for any pair of basis functions in the set B, then we say that these basis functions they are all orthogonals in that set. So, transform coefficients in orthogonal expansion that could be easily computed by exploiting this property. That is one of the usefulness of this particular property, and you can see that simply if I take the inner product of the function with a basis function, then we can and also divide it by Ci, then we can get the corresponding lambda i's. And if Ci is equal to 1, then it becomes orthogonal, orthonormal expansion. Then we can simply write lambda I equal to inner product of function and Bi. So, this is what since we are expressing the functions in terms of only transform coefficients. So, we call this operation is a forward transform operation. So, now function instead of being represented by f x, now the function is represented by these lambdas, and the reverse transform or inverse transform would be to compute the function from these coefficients back, and because of the orthogonal property and also orthonormal property, we can simply write it in this form. That means, simply it's nothing but the linear combination of those basis functions, and since it's a continuous domain, so we are taking the integrations over all the index values. Otherwise, in the discrete domain, we can write it in this form. So, one of the special case of this orthogonal expansion is Fourier transform, and in this case you can see that the set of basis functions is given by in this form. It is a complex sinusoid which is a member of this set. It is given in this form, and the completeness of this basis function is that, see, any orthogonal set, if I take a subset of any orthogonal basis set, that subset will also remain orthogonal, but using that subset, using the linear combination of that subset, you will not get the complete reconstruction of the function. The basis set which gives the complete reconstruction, that is called the complete base. So, in the Fourier transform, in fact, the set what is defined here, it is a complete base, because it can give me back this function as a linear combination of this function. You can see that actually this is a infinite set, though individually every sinusoid can be distinguished here. So, the orthogonality property is reflected by these particular relationships, where you can see that delta x is a unit impulse function, and whose area is equal to 1 centering at omega equal to 0, and otherwise delta x value would be 0 in everywhere. So, it is an unit impulse function, and this particular property gives you the orthogonal property of the Fourier transform, this base. So, Fourier transform can be defined in this form. This is a forward transform. As you can see, this is the inner product of this f x and also the complete base. So, the base is e to the j omega x. Here there is a little bit of correction is needed. It is actually e to the power j omega x. So, you take the complex conjugate of the base, which is e to the power minus j omega x. And if I take the inverse transform, then once again this is considered as the inverse transform is this should be f j omega. There is an error here also. We will correct it in the slide later on. So, f j omega is the corresponding coefficients, and the linear combination of this basis function will give you the corresponding inverse transform. So, it gives you the full reconstruction because it is a complete base, as I mentioned. One of the interesting fact that can be noticed here, that this complex sinusoid, it can be defined, it can be decomposed into two real and imaginary parts. Real part consists of cos omega x, and imaginary part consists of, say, minus sin omega x in this case. So, this forward transform can be expressed in this form from this expression itself. So, it has one transform component which consists of real part, another transform component which consists of imaginary part, and in the real part we are using the basis functions as cos omega x, whereas in the imaginary part we will be using the basis functions at sin omega x or minus sin omega x, whatever be your interpretation. So, we can consider cos omega x as the set of basis functions, and this is also orthogonal. This trigonometric functions, this is also orthogonal, we know, and sin omega x, this is also orthogonal. But the thing is that, as I mentioned, that they won't form the complete base. So, if I use only cos omega x, we can if I use f j omega cos omega x, the real part of cos omega x, then that won't give me back the full function. Similarly, if I use the corresponding imaginary part of the transform and use the sin omega x, that won't also give me back the full function. So, it is not a complete base. But there are certain functions where actually if you use only cosine functions or sine functions, you can reconstruct it fully. So, these functions are called even and odd functions. There is a property like for an even function, it should satisfy this property, that it should be symmetric around the around origin or around the at x equal to 0 at both ends. See, f minus x should be equal to f x for all x, whereas for odd it should be antisymmetric when it is f minus x equal to minus f x for all x, and naturally at the at x equal to 0, the value has to be equal to 0 from this definition. So, a function could be even, it could be odd, or it could be neither. When they are when they have these properties, then you can expand them using only cosine or only sine functions. So, let us see. So, for even f x, we can have, this is a property which is satisfied, because in that case, if I take the integrations by taking the product with sin omega x, that would be 0. So, all sinusoidal terms would be 0. So, that is why only cosine terms will remain, and your transform will be sufficient. Your transform coefficients can be sufficiently described by only cosine transformations. Similarly, for odd f x, this property is true, and that is why using only sinusoidal basis you can reconstruct it. Now, this could be easily derived if I consider the definitions of, if I consider these relationships of cos theta and sin theta in terms of the complex quantities, exponential quantities. So, full reconstruction is possible with cosines or when the function is even, and with sines when the function is odd. Now, let us consider the discrete representation. So, a discrete representation of a function can be made in this form, that the function needs to be sampled at periodic interval, and it would provide a sequence of functional values, and where each sequence position is an element of the integral grade, integral integer set, and a sampling interval, there is a sampling interval which is associated with this particular definition. So, it can be also considered as a vector in an infinite dimensional vector space, but in our consideration, since we will be always using images of finite dimension or signals of finite dimension, we are representing them in the computer, in the computation, in the discrete domain. So, there we will be having only a finite dimensional vector, and for example, we can represent a function from within certain interval from say 0 to n minus 1. You should note here the sampling interval is implicitly represented in this form. So, even without sampling interval, we have a representation of the function, and when we are trying to interpret the function with the physical terms, physical quantities in the functional space, then only the sampling interval has to be used. So, let us consider that we are representing our function in this case with a finite dimensional vector and say in this case it is an n dimensional vector. It is a column vector representation. So, that is why the transpose operation has been used here. So, then how do you define a discrete linear transform? It is very simple, because you know that whenever we perform any matrix multiplication in this form, say you have a column vector of n dimensional column vector, and let there be a matrix of m cross n dimension, and if I multiply them, then you will get another vector of m cross 1 dimension, that means m dimensional vectors. So, this is the transformation of this column vector into another column vector of a different dimension. So, this is what is in general a transform, and we call it a linear transform, or in the discrete, since we are using the discrete representation, let us call it as discrete linear transform. And this transform, it is inverse when this matrix, which is called say transformation matrix B, is a square matrix and also invertible. So, one of the interesting facts about this transformation matrix that we can note, that we can consider rows of this transformation matrix, they form the basis vectors. This is the analogy with respect to the basis functions, because we will see instead of inner product of between two functions, we are having here inner product of two vectors, which is equivalent to the dot product of two vectors. So, let us consider this, say this is the representation of the transformation matrix, and these are the row vectors which is indicated by these transpose operations, and you can see that this is the row vector we are considering. These are the complex conjugate operations by keeping it consistent with the representation what we have for the inner product. So, when we make a when we perform this dot product or inner product between two vectors, then you get the corresponding element. So, ith basis vector provides you the ith element of the transformed vector, which is y here. So, the orthogonality condition in this case is reflected in this form, that if you take any pair of two basis vector, then their inner product should be equal to 0 if they are different, otherwise they should have a non-zero value C I. So, with this form we can consider it will have the similar representations of you can consider that a function as a linear combination of all those basis vectors. So, if I look at the discrete Fourier transform expressions, the basis vectors for the discrete Fourier transforms are represented in this form. So, it is 1 by root n e to the power j twice pi k by n capital N into n. You should note here this is defined for n functional points. So, bkn is a small nth element, which means we can form a basis vector from by computing it n equal to 0 to n equal to n minus 1 at each integer value of n within this interval. So, that gives me a vector that is a kth vector, and there are n such vectors where the indexes vary from 0 to n minus 1. So, in the forward transform of this forward transform or discrete Fourier transform of a sequence f n, discrete sequence f n, that is a finite sequence of length n, can be expressed in this form. You can find out that this is nothing but the inner product of this. Only thing is that instead of putting 1 by root n, 1 by root n here in this expression, we have taken care of instead of doing the square root operation, we performed just 1 by n, that is a simple operation during the inverse transform. So, we kept this division normalization operation, we removed that operation here and included it in during the reconstruction. So, actually the value what you will get, that will be proportional. It does not matter at this stage, but when you reconstruct it, it will again recover the same value, because you are taken care of that particular normalization here. So, the reconstruction also you can see that In this case, it is a linear combination of the corresponding basis vector and the coefficients which is given by this. These coefficients are the coefficients from discrete Fourier transform. So, in fact, this expression, from this expression we can also observe that discrete Fourier transform is nothing but Fourier series of a periodic function. So, let us consider a finite sequence. So, in this case, for simplicity, let me take only 4 functional values, and so which means my value of capital N is 4 here, and this is the functions for which I will be doing discrete Fourier transform. So, what I will consider, because there is no definitions outside this interval, I can use any definition as per my convenience, any other functional values, and perform a transformation, and after inverse transformation once again I will keep my observation window within the interval from this 0 to say 3 in this case. So, a periodic extension of this signal could be in this form, that means it is repeated. So, that in a periodic function this property needs to be satisfied. A periodic function with a period capital N should be f small n plus n should be equal to f n. So, that is satisfied, as you can see here. Here the value of capital N is equal to 4. So, we will see after every 4th sample again it is repeating the same value. So, it becomes a periodic signal, and as you know, any periodic signal can be expressed as a linear combination of sinusoid functions, and you can perform Fourier series. That is what you are doing here in this case, and after that you are basically while in performing inverse Fourier transform, you are only performing for at these 4 sample points. So, and just to note that how it is related with the actual physical sampling interval, which is say x naught here. So, the fundamental frequency would be determined by the period length of the period of this signal, which is capital N into x naught. So, fundamental frequency is 1 by n x naught, and you can see that harmonics is represented by here k harmonic k by n. Actual implicitly there is k by n x naught, that is the physical frequency. So, we call k by n as the normalized frequency in this representation. So, discrete Fourier transform, that can be also expressed in terms of a linear transforms, which means we can express a discrete Fourier transform as a matrix multiplication of a column vector, where the column vector is given by the functional values, a finite dimensional vector as we have considered earlier, and if I multiply this matrix, then we will get the transform matrix. And you can see that these elements, they are obtained from this corresponding basis vectors definition. So, we can represent this matrix in a shorter form, where each k and nth element is represented by the corresponding expression, this expression, and if the value of k and n, they range from 0 to n minus 1, which will give me an n cross n matrix. So, in a forward transform, what we are doing, we are simply multiplying this transformation matrix with the column vector f, which is representing this particular column vector, and then we get the output transform matrix. So, this transform column vector, which is representing this column vector, which is actually the coefficients of discrete Fourier transform. And inverse transforms will be naturally, if I take the inverse of f n and multiply with f, then we will get back once again column vector. Incidentally, because of the orthogonality property and also orthonormal property of these functions. So, you can show that the inverse of the discrete Fourier transform matrix is nothing but this is the Hermitian transpose of the corresponding matrix. Hermitian transpose is the transpose of this matrix, and also the element should be also complex conjugate of the you should have to perform also complex conjugate operation, that would give you the Hermitian matrix. Now, discrete, there could be other kinds of set of orthogonal basis vectors, and some of them could be derived or extended from discrete Fourier transform representation. So, we call it generalized discrete Fourier transform. If you can observe that in the discrete Fourier transform, basis vectors are generated from the complex sinusoid by sampling the complex sinusoid within an interval between 0 to n minus 1, and then we have sampled at a regular interval. Now, if I make a phase shift there in that interval, so there itself we will have we can have a variation instead of we can do a phase shift of beta, and also while defining basis vector we have considered harmonics and we have generated harmonics at regular interval. So, if I give also a shift in the frequency space, then also we can have a different basis vector. Now, these basis vectors, this representation, it will generate also n basis vectors of n dimensions, and that would be once again an orthogonal basis vector, which is a square matrix which could be invertible. So, it could be easily used for once again for making a transform. So, there are, this is a generalized discrete Fourier transform. We can use these basis vectors and we can get these expressions for discrete Fourier transform. Similarly, we can get back the function by applying the inverse Fourier transform. It is a similar form what we did for the case of discrete Fourier transform, and the corresponding transformation matrix can be expressed in this form. Here the elements, as you can see, it retains the same similar expressions, only there are parameters alpha and beta which is giving you a different set of transformation matrix. There are some popular transformation matrix, as you can see, a special value of alpha at 0 and beta, that itself will give you the discrete Fourier transform what we discussed earlier. If I took alpha equal to 0 and set beta equal to half, we call that transform as odd time discrete Fourier transform or OT-DFT, and we can represent the transform in this form. Similarly, alpha equal to half and beta equal to 0 would be odd frequency discrete Fourier transform, and if both are half, odd frequency odd time discrete Fourier transform. There are different properties which I am not discussing here, just for your example we have given this particular thing, and they have their inverse transform in this case also. Those are related, I have shown you in this particular grid. So, there are different relationships of the inverse transform. I think let us stop here at this point, and we can start from this point in the next lecture, where we will see that though it is not possible in the continuous domain to have cosine transform and sine transform for every kind of function, but in discrete domain for any finite dimensional sequence you can define cosine transforms and sine transforms. So, for that we will be using this generalized discrete Fourier transform. So, thank you for listening this talk, and we will move over to the next lecture. Thank you.